Welcome back to the video course on fluid mechanics. In the last lecture, we were discussing about the exact solutions for the Navier-Stokes equations. So, the Navier-Stokes equation which we have derived earlier for the viscous flow, we have seen it is second order nonlinear equations. So, only for simplified cases only we can derive the exact solutions. So, we have seen few cases like plain Poisson flow, Q-tape flow, and then now also we have seen say a simple transient type case where an exact solution can be derived for the Navier-Stokes equations. Now, in this lecture further we will discuss few more say the exact solutions which are possible for the Navier-Stokes equations. These problems are again some more simplified cases. So, first we will see the case of pipe flow, the steady state flow in pipes. So, this case is called Hagen-Poisson flow. So, let us consider the flow through a straight pipe of constant circular section. So, here we can see here there is a pipe section. So, this is long pipe and the radius is R, capital R. So, for the circular section, as we have already seen, so we have seen the Navier-Stokes equation in two forms. One is the Cartesian coordinate forms and the second one is the cylindrical coordinates forms. So, pipe is concerned, we are dealing with the radius, length of the pipe and the angles with which we consider. So, the cylindrical coordinate system will be better for this type of problem, say for the Hagen-Poisson flow problem. So, here R is the radius of the pipe, theta is the angle which we consider at any particular location and then the length of the pipe which we consider. So, here corresponding to the Cartesian coordinates of x, y and z we consider r, theta and z, and corresponding to the velocity components u, v, w in x, y, z direction we consider v r, v theta and v z. So, correspondingly with respect to this figure we can write x is equal to r cos theta and y is equal to r sin theta and z is equal to z. So, that we can write now this u is equal to v r cos theta, v is equal to v r sin theta and w is equal to z. So, this is the problem structure which we are trying to apply the Navier-Stokes equations and then trying to get an exact solution for this kinds of problem, the flow through pipes which is steady state flow, that is Hagen-Poisson flow. So, now here for this particular problem, since the pressure variation, pressure is a function of Z only, that means how the with respect to the length of the pipe only the pressure is varying. So, that we can write del P by del R and del P by del theta, they both are 0. So, that we can write del P by del R is equal to del P by del theta is equal to 0. So, pressure is a function of Z only. So, now let us consider the axial component of the Navier-Stokes equation in the cylindrical coordinates. So, we have seen earlier the Navier-Stokes equation cylindrical coordinates we can write r, theta and z components, 3 components. So, here we consider the axial component of the Navier-Stokes equation in the cylindrical coordinate system. So, as we have seen earlier, so this equation the axial component can be written as del V z by del t plus V r into del V z by del r plus V theta by r into del V z by del theta plus V z into del V z by del z is equal to F z minus 1 by rho del P by del z plus nu the kinematic viscosity into del square V z by del r square plus 1 by r into del V z by del r plus 1 by r square plus del square V z by del theta square plus del square V z by del z square, where F z is the body force component for the problem considered. So, here we consider as in the previous figure we consider horizontal pipe like this. So, that we do not have to consider the body force for this particular problem and we consider the flow to be steady state. So, that the del V z by del t term, the time dependent term vanishes or it is 0 and then as the velocity v z in the z direction is varying with respect to the radial direction. So, v z is a function of v z r and p is a function of p z and partial derivative can be replaced by ordinary derivative. So, that now this equation, so the time component is gone, and then we can just simplify this equation with respect to the various assumptions used here. We can write as dp by dz is equal to mu into del square vz by del r square plus 1 by r into dvz by dr. So, the final equation becomes dp by dz is equal to mu into d square vz by dr square plus 1 by r dvz by dr. So, now here for this particular problem, for this pipe flow problem, we can see that say pipe is concerned all the say on the boundary, that means due to no slip condition at r is equal to capital R, we can write Vz is equal to 0. That means on the pipe boundary the velocity is 0. So, that Vz is equal to 0 at r is equal to r, that gives one boundary condition, and then we can see that for pipe flow as described here, you can see that the velocity variation is parabolic and maximum will be at the center of the pipe. So, that here at this location at r is equal to 0, we can write dvz by dr is equal to 0. Since maximum velocity is at the center line, so at r is equal to 0, we can write the derivative of the velocity with respect to r dvz by dr is equal to 0. So, now for this particular problem we have simplified the Navier-Stokes equations, and then we have derived the boundary conditions. So, now for the simplified problem we will be trying to find out an exact solution with respect to the various conditions here. So, here our aim is to find out the velocity. So, in order to find this velocity here with respect to this earlier equation which we derived here. So, here we will integrate equation number 2. Let us assume dvz by dr is equal to s. So, that we can write equation number 2 in terms of this s as ds by dr plus 1 by r into s is equal to 1 by mu dp by dz, equation number 3. So, now here from the mathematical textbooks we can assume integration factor if I is equal to e to the power integral 1 by r dr. So, this is equal to e to the power log e r, that is equal to r. So, we assume an integration factor if as I is equal to r. So, now we will multiply both sides of equation number 3 by this integration factor, and then we will use the integrating by parts rule on the left hand side of this equation. So, finally, by multiplying by the integrating factor if, and so given I is equal to r, and then using the integration by parts, we can write this equation number 3 as r into s is equal to integral 1 by mu dp by dz r dr plus C1, where C1 is a constant of integration. So, this again we can write as Rs is equal to 1 by mu dp by dz r square by 2 plus C1. So, finally, this equation number 3 is transformed as this equation here. So, now also we can write r. So, now after substituting for this s here, we can write r into dvz by dr is equal to 1 by mu dp by dz r square by 2 plus C1 as in equation number 4. So, now we have the boundary conditions, so that we can find out the constant of integration. So, here say at the central line the velocity is maximum, so that dvz by dr is equal to 0 at r is equal to 0. So, that in this from this equation number 4 we will get C1 is equal to 0. So, then integrating this equation for again and substituting as s as we have already seen, we get Vz is equal to 1 by mu dp by dz into r square by 4 plus C2 as in equation number 5. So, again here the C2 we can find out by using the boundary condition. At r is equal to r, we have the velocity is 0. So, that we will get C2 is equal to minus 1 by mu dp by dz into r square by 4. This r is the capital R is the radius of the pipe. So, finally, we get here this constant of integrand C2 as C2 is equal to minus 1 by mu dp by dz r square by 4. So, after substituting finally, we get the velocity distribution Vz is equal to 1 by 4 mu dp by dz into r square small r square minus capital R square. So, this expression equation 6 gives the velocity distribution at various locations. So, small r is the distance from the center line. So, at various locations we can substitute and get the velocity distribution as Vz is equal to 1 by 4 mu dp by dz into r square minus capital R square, where capital R is the radius of the pipe. So, like this we can derive the velocity distribution as far as the pipe flow is concerned. So, now once we get this, we can derive the various other parameters like discharge and other parameters. So, here this equation for V velocity distribution, we can write V is equal to minus 1 by 4 mu dp by dz into r square minus r square, equation 6a. So, the maximum velocity occurs at the center and is given by, so here we can substitute r is equal to 0. So, that gives u max is equal to minus 1 by 4 mu dp by dx into r square as in equation number 7. So, if you use equation number 6a and 7, so here we assume the longitudinal direction coming back in this direction, longitudinal direction. So, u is equal to, we can write the velocity variation, u is in terms of the maximum velocity, u is equal to u max into 1 minus r by r whole square as in equation number 8. So, this equation 8 is the most commonly used equation for the velocity distribution for laminar flow through pipes. So, here our assumption is that flow is steady state and then laminar and say the pipe is parallel horizontal direction. So, all these assumptions we applied, and that way only we could use the Navier-Stokes simplified form of the Navier-Stokes equation to derive an exact solution. So, now once we get the velocity distribution, we can find out the discharge. So, the discharge through an elementary ring of dr thickness at radial distance r is dq is equal to u into 2 pi r dr. So, we can write dq is equal to, with respect to after we substitute for u, dq is equal to u max into 1 minus r by r whole square 2 pi r dr. So, total discharge we can integrate integral dq. So, that is equal to integral 0 to r u max 1 minus r by r whole square into 2 pi r dr, that is equal to pi by 2 into u max r square, and average velocity. So, once we get the discharge, average velocity we can find out by just dividing by the area of cross section. So, u bar, the average velocity u bar is equal to q by a. So, from this expression we can write q by a is equal to pi by 2 u max r square by pi r square, that is equal to u max by 2, that is equal to minus 1 by 8 mu dp by dx into r square. So, this will be the average velocity and the pressure difference between the two sections. So, now we have found the velocity distribution, we got an expression for velocity and then we derived an expression for the discharge, and then if you want to find out the pressure difference between 2 points, 2 sections, we can just use the equation. So, P1 minus P2, since our earlier velocity equation is with respect to the pressure, so that we can write P1 minus P2 is equal to 8 mu u bar by r square into x2 minus x1, that means the distance from one section to another section. So, that is equal to 8 mu ul by r square. If the distance between section 1 to 2 is L, so that we can write P1 minus P2 is equal to 8 mu ul by r square. So, this we can write in terms of diameter as this is equal to 32 mu u bar L by d square. So, like this, now what we did here is the Navier-Stokes equation we simplified for the given conditions, and then we, with respect to boundary condition, we derived an exact solution for the velocity, and from the velocity we can determine various other parameters like pressure variations from one section to another, and then we can find out the discharge. So, like this we can utilize the Navier-Stokes equation for the simplified case, and then we can derive an exact solution for the problem. So, this way two more other problems we will discuss here. So, this case is the Hagen-Poisson flow, where we derived the expression for the velocity variation. we have seen the pipe flow. So, now we will derive, we will check some more, we will try to derive the exact solution for two more other problems. So, another typical problems which is generally used in mechanical engineering is flow between concentric rotating cylinders. So, this is a very common problem in mechanical engineering. So, our problem is that there are two rotating cylinders and a fluid is between these two rotating cylinder. So, our aim is to derive an expression for the velocity variation for the rotating cylinder. So, we will start with the Navier-Stokes equation, we will apply all the simplifications and then we want to derive an analytical solution. So, here the problem is we will consider a flow of fluid contained between the two concentric cylinders as shown in figure. So, here this is the first cylinder of radius r1 and here this is the second cylinder of radius r2 and the flow is between these two cylinders and both the cylinders are rotating like this with first one with the angular velocity of omega 1 and the second one with an angular velocity of omega 2. So, angular speed of the cylinders are omega 1 and omega 2 and radius are r1, radii are r1 and r2 as in figure. So, this kinds of problem after sufficient time, if once we start the machine, it may be transient in nature, the flow problem may be transient in nature, but after some time the problem flow becomes steady state. So, that we can assume the case of steady state here for this typical the flow of rotating cylinders, concentric rotating cylinders. So, now if the spacing r2 minus r1 is small, so strictly speaking the Reynolds number r is equal to rho into omega 2 minus omega 1 into r2 minus r1 square divided by mu if it is less than or equal to 1 and you can see that the 1D flow the flow is we can consider as one dimensional flow in angular direction, that is say for this typical problem. So, we can consider the flow as 1D flow in angular direction. So, now if we assume here if Reynolds number is less than or equal to 1, as at high Reynolds number flow become unsteady and 3-dimensional turbulent. So, we are considering this case only for Reynolds number less than or equal to 1, since when we consider the higher Reynolds number the flow is generally unsteady and then we have to consider 3-dimensional and turbulent flow depending upon the case. So, here we consider the Reynolds number as say less than or equal to 1 and here let the velocity vector u correspondingly in x, y, z direction u, v, w be the components of velocity in r theta and z directions. So, here the velocity component in z r theta and z direction we are writing as u, v and w. So, the cylinders are assumed to be long, having no flow, no through flow and end effect. So, here for this typical problem, before using the Navier-Stokes equation and simplifying and trying to get an exact solution, we assume that there are no end effects and then the flow we are having no through flow and we can write in this typical case w is equal to 0 and all derivatives of w is equal to 0, where w is the velocity component in the z direction for this typical problem. So, now due to the rotation symmetry. So, here in the previous slide you can see that there is symmetry with respect to the rotation. So, due to the rotational symmetry we can write del u by del theta is equal to 0. So, in internal flow problems with a constant area of cross section, pressure can at best decrease in the flow direction for this kinds of problem. However, the flow path in the annulus is a closed curve and we require pressure at point to be unique irrespective of times the closed curve has been traversed. So, these are the assumptions which we use for this problem. So, this tells that the pressure must be constant in the annular gap. So, we are using certain assumptions like del u by del theta is equal to 0 and then say we assume that the flow path in the annulus is a closed curve and then we also assume that pressure must be constant in the annular gap. So, for these conditions now we simplify the Navier-Stokes equation. So, as we have already seen, the flow is we are assuming the flow is to be steady state and then various assumptions we have seen. So, now if we utilize all these assumption, then we can write the Navier-Stokes equation cylindrical coordinate with the mentioned simplification. In the r direction we can write rho v square by r is equal to dp by dr, and then in theta direction, say we can write the second derivative of the velocity d square v by dr square plus 1 by r dvr minus v by r square is equal to 0. So, this two subscript shows the second derivative and this is the first derivative. So, v r r plus 1 by r v r minus v r square is equal to 0. The flow is subject to no slip boundary condition. So, that we can write at r is equal to r 1, v is equal to omega 1 r 1, and at r is equal to r 2 we write v is equal to omega 2 r. So, these are the boundary condition for this problem, and the governing these Navier-Stokes equation are simplified in this form. So, now this we have already seen, as we have in the previous case. Here we have this equation theta direction, we have got a second derivative of the velocity. So, we can integrate twice this equation, and then there will be two constants C 1 and C 2. So, finally, we can get a solution V r is equal to 1 by r into C 1 into r square by 2 plus C 2. So, this is the expression for the velocity variation for this typical problem. So, here the problem is like this. So, here we have already seen this r is the difference between this r 2 to r 1. So, that is what we are, r small r is between the difference between r 2 to r 1. So, the solution, finally the solution becomes V r is equal to 1 by r C 1 into r square by 2 plus C 2, and C 1 we can obtain, we can, here two boundary conditions are there. So, we can use these boundary conditions and get the constant C 1 and C 2. C 1 is equal to 2 into omega 2 r 2 square minus omega 1 r 1 square divided by r 2 square minus r 1 square, and C 2 is equal to minus omega 2 minus omega 1 r 1 square r 2 square divided by r 2 square minus r 1 square. So, like this we can derive the expression, derive an expression for the velocity variation for the flow between the two concentric cylinders. So, here what we did is we applied various simplifications for the problem, and we got a simplified form of the Navier-Stokes equation, and then we integrated the equations so that we can get a solution. So, finally, we got a solution for the velocity variation, and then that can be used to find out various other parameters. So, this kinds of problem there is application to a viscometer. So, here how we apply this solution to a viscometer. So, application to a viscometer. So, viscometer measures the viscosity of a liquid. So, here the next slide shows how a schematic sketch of the viscometer. So, this is a schematic sketch of the viscometer. So, here now it is a typical arrangement of a stationary inner cylinder. So, that we can assume omega 1 is equal to 0, the angular velocity omega 1 is equal to 0, and rotating outer cylinder. So, hence the velocity profile. So, with respect to our earlier equation which we derived here. So, the velocity profile we can write V is equal to omega 2 r 2 square divided by r 2 square minus r 1 square into small r minus r 1 square by r. So, and then we can get the wall shear stress on the inner cylinder can be derived as by using Newton's second law, Newton law of viscosity. Here we have got V. So, then we can use the Newton's law of viscosity to get the wall shear stress on the inner cylinder. So, tau W is equal to mu into r d by dr of V by r. So, that is equal to mu dV by dr at r is equal to r 1. So, we get an expression for the wall shear stress on the inner cylinder as 2 mu omega 2 r 2 square divided by r 2 square minus r 1 square. So, like this, once we get the velocity, we can find out various parameters like shear stress on the wall and other parameters. So, this now what we derived for the concentric cylinder problem, the velocity expression we directly utilized for the viscometer, which we have already seen. So, here for what the torque can be measured by a torsion wire. So, here the problem is the viscometer problem. Here we have, it is, this cylinder is suspended with respect to a wire here. So, this torque can be measured by a torsion wire whose stiffness is known. So, knowing the geometry of the apparatus, the viscosity can be determined from the formula K theta is equal to 4 pi r1 square r2 square divided by r2 square minus r1 square into mu omega 2 into L, where theta is the angular deflection and k is the torsional stiffness of the wire. So, like this we can find out the other parameters for these kinds of problem. So, here we applied the equation derived for the flow between the concentric cylinders, two concentric cylinders, and then we got the expression for the velocity and the shear stress and other parameters for these kinds of problem. So, this is a typical problem which we started with the Navier-Stokes equation and then simplified the equations, and then we derived the expression for velocity and other parameters. So, finally, before closing these exact solutions for Navier-Stokes equation, we will consider one more example. So, here the example problem is the statements like this: a liquid flow down a wide inclined plate laid at an angle theta with horizontal. So, the depth of the liquid normal to the plate is h. Assume steady flow under the influence of gravity and parallel to the plate. The effective viscosity of air at the free surface is negligible. Then we have to find out the velocity profile in terms of the viscosity mu, mass density rho, the h and theta, and also we have to find out the shear stress at the boundary and the average velocity of the flow. So, this is the problem. So, here the problem is defined in this figure. So, here we have got an inclined plate and a flow is taking place above the plate, and then the thickness of the flow is h, and the angle of inclination of the plate is theta. So, here comparing to the earlier problem like a plain Poisson flow or the other kinds of just flow over a say plate, earlier problems which you can. So, here the plate is inclined. So, we have to consider the body force. So, this typical the problem is we have to consider the body force, this kinds of problem, and then here our aim is to use the Navier-Stokes equation. Then we will simplify the Navier-Stokes equation, and then we want to get an exact solution for this kind of problem. So, the solution, as the plate is wide and the z direction need not to be considered. So, you can see that we consider wide plate. So, this z direction need not to be considered, and here we assume the flow to be steady. So, del by del t time is equal to 0. So, flow is steady. So, the transient time becomes 0, and then we assume that the flow is parallel to the plate. So, that is x axis. So, we can write del u by del x is equal to 0. So, that u y is equal to 0. So, this is the third assumption, and then also the pressure gradient dp by dx is equal to 0 as the flow takes place at a constant depth h. So, these are the assumptions. So, for the problem. So, once the problem statement is known, so we are trying to see that what are the assumptions we can put forward such that we can simplify the governing equations with respect to the various assumptions. So, here for this typical problem we are assuming the flow is to be steady, and then flow is parallel to the plate, and then the pressure gradient is del p by del x is equal to 0. So, these are the assumptions, essential assumption for this problem, so that we can simplify our equation. But here we cannot neglect for this compared to the earlier problems which we discussed. Here the body force cannot be neglected. As I mentioned, the plate is inclined. So, for the inclined plate you can see that there will be always the body force effect will be there, and then if z is the vertical direction, the potential per unit mass due to the body force we can write as Gz. So, here we can see that with respect to this figure we can write the potential per unit mass due to body force is Gz, and then finally the components of the body force in x and y direction we can write as in the body force in x direction is minus del g z by del x. So, that can be written as minus del g, the acceleration due to gravity in del z by del x is equal to g sin theta, and y is equal to minus del g z by del y. So, that is equal to minus g cos theta. So, now we use all these assumptions, and finally we can get the Navier-Stokes equation in the following form. So, the Navier-Stokes equation become g sin theta plus nu d square ux by dy square, where nu is the kinematic viscosity, equation number 1, and second equation is minus g cos theta minus 1 by rho dp by dy is equal to 0, equation number 2. So, here due to our assumptions, all other assumptions like steady state and the flow is parallel to the plate and the flow width is large, so that we can consider the z direction need not to be considered. So, all this, due to all these assumptions, all other terms we can neglect, and finally, we have simplified the Navier-Stokes equation in the form of equation number 1 and 2. So, now our aim for this problem is to find out the velocity distribution u x. So, here you can see that the equation is say d square u x by, in terms of d square u x by dy square. So, as we did in the previous case. So, we will see what are the boundary conditions, and then we will go for integration such that you will get the expression for the pressure and velocity. For steady uniform flow parallel to the plate at a constant depth h, we have already seen del by del t is equal to 0, del u by del x is equal to 0 and u I is equal to 0 and dp by dx is equal to 0, del p by del x is equal to 0. So, from equation number 2, this equation number 2, we can write dp by dy is equal to minus rho g cos theta. So, this equation number 2 we can integrate such that we get p is equal to minus rho g by cos theta plus c, the constant of integration. So, we get an expression for the pressure in terms of the depth y. So, p is equal to minus rho, the rho is the density of the fluid. So, minus rho g into y into cos theta plus c. So, here we, to find out the c, we will use the boundary condition. So, at y is equal to h, p is equal to 0 because the pressure is atmospheric. So, that we can write c is equal to rho g h cos theta. So, now if you apply this c here in this equation, we get p is equal to rho g cos theta into h minus y. So, this is the expression for this problem. We got an expression for the pressure as p is equal to rho g cos theta into h minus y. So, the standard procedure of integration we used, and then we applied the boundary condition to get the expression for p. So, now this expression 3 gives the pressure distribution for the flow. So, our aim is to get the velocity distribution also. So, from equation 1 we can integrate twice with respect to y, that gives dux by first integration gives dux by dy is equal to minus g sin theta by nu into y plus c1, equation number 4, and once again integrating we get ux is equal to minus g by nu into sin theta into y square by 2 plus c1 y plus c2. So, finally, we got equation number 5. So, here we have got constant of integration c1 and c2. So, we can utilize the boundary conditions. So, the boundary conditions are at y is equal to 0, ux is equal to 0, which gives c2 is equal to 0, and at y is equal to h, dux by dy is equal to 0. So, that which gives c1 is equal to gh sin theta by nu. So, finally, we can get an expression for velocity as ux is equal to minus g by nu sin theta into y square by 2 plus gh by nu sin theta into y. So, after substituting the boundary condition, we got c1 and c2 the integration constants, and then we got finally the expression for the velocity as ux is equal to minus g by nu sin theta y square by 2 plus gh by nu sin theta into y. So, now this can be simplified as ux is equal to g sin theta by 2 nu into 2 hy minus y square, or we can write ux is equal to rho g sin theta by 2 mu 2 hy minus y square. So, this is the final expression for the velocity for this particular problem. We got the velocity variation as rho g sin theta by 2 mu into 2 hy minus y square, and then once we get the velocity, we can use Newton's law of viscosity to get the shear stress. So, shear stress at the boundary, we can write rho 0 is equal to mu into dux by dy at y is equal to 0. So, that gives mu into g sin theta by nu into h minus y at y is equal to 0, that gives rho g h sin theta. So, finally, we got the expression for the shear stress at the boundary, tau 0 is equal to rho g h sin theta. So, tau 0, this is the formula for the tau 0 is rho g h sin theta, this is the formula for the shear stress at the boundary. This is a very important relation used in involving problems like sediment transport in open channel. Using this expression, we can see how the settlement of the sediments takes place. So, sediment transport problems open channel, we can use this expression, and then if you want to find out the average velocity of flow for this particular problem, V is equal to Q by H. So, where Q is the flow per unit width. So, flow per unit width Q is equal to integral 0 to h ux dy. So, that is equal to integral 0 to h rho g sin theta by 2 mu into 2 h y minus y square dy. So, from this expression we will get Q is equal to rho g h cube sin theta by 3 mu, and the average velocity V, capital V is equal to rho g h square sin theta by 3 mu. So, these are the various expressions. So, finally, by using various assumptions, we simplified the Navier-Stokes equations, and then we got the simplified form of the Navier-Stokes equation. Then we integrated to get the expression for the velocity, and then we found the other parameters like shear stress and then discharge per unit width by so the various constants of integrations were found by using the boundary condition. So, like this various problems can be attempted, say like wherever possible, say wherever we can simplify the Navier-Stokes equations, and the problem is so simple that we can try for analytical solutions by putting forward various assumptions and then using the boundary conditions. So, like this few more exact solutions are available for the Navier-Stokes equations, but we will not discuss further since we have already seen few typical cases. So, before further going to the applications of Navier-Stokes equation, we will here discuss different formulations for Navier-Stokes equations. So, we have seen the most commonly used formulation of the Navier-Stokes equation, which we have derived earlier in 2 dimensions, and then we extended the equations to 3 dimensions. So, but in literature, if you go through various research papers and various literature on the Navier-Stokes equation, we can see few more other kinds of formulations for the Navier-Stokes equation. So, these different formulations have been derived by using various assumptions, and we can see that commonly 3 typical formulations are used in literature. First one is the primitive variable formulations, or it is velocity pressure formulation. So, that is what we have discussed and we have derived earlier. So, here the formulation is in terms of velocity and pressure. So, the equations, the Navier-Stokes equations are in terms of the velocity and pressure. So, the variable, the primitive variables are used like velocity and pressure. So, that is why the formulation is called primitive variable formulation. And second kind of generally used formulation is called velocity vorticity formulation. So, here the formulation for the Navier-Stokes equations are in terms of velocity and vorticity, and then third commonly used Navier-Stokes equations are in terms of vorticity and stream function. So, it is called a vorticity stream function formulation. So, here the vorticity is defined as del cross u bar, where u bar is the velocity vector. So, like this, so 3 typical formulations, commonly 3 formulations are used in literature. So, we will see the various equations used for all these 3 formulations. The first one is the velocity pressure formulations. Already we have derived the equations. So, the equations, say for example, if you consider in 2-dimensional case or for 2-dimensional problems, the equations are the continuity equation given by del Ux by del y plus del V by del y is equal to 0, and then we have two momentum equations, so which we have already derived. So, here the equations are rho into del u by del t plus u into del u by del x plus v into del u by del y is equal to minus del p by del x plus rho g x plus mu into del square u by del x square plus del square u by del y square, and third equation is rho into del v by del t plus u into del v by del x plus v into del v by del y is equal to minus del p by del y plus rho g y plus mu into del square v by del x square plus del square v by del y square. So, these three equations, including the continuity equation and two momentum equations, are the equations used in the velocity pressure formulation for the Navier-Stokes equation, and these equations are called primitive variable formulations, and this is the most commonly used Navier-Stokes equation for most of the fluid flow problem. And then the second one, the velocity vorticity formulations. So, here we transform the, say, as we have already derived the primitive variable formulation, that we can transform in terms of the, say, another component, another important variable called vorticity. So, finally, we get the equations in terms of velocity and vorticity. So, if we consider three dimensional formulation, then we can say if the velocity vectors are u, v and w, and the vorticity vectors are psi, eta and epsi as written here, then the equations, I am not going to the derivations of these equations. The derivations of the equations you can see various fundamental books where the Navier-Stokes equations are derived and other research papers. So, finally, the equations are generally expressed like this. This is first one is the vorticity transport equation. So, del omega by del t. So, here omega bar is the vorticity vector. So, del omega bar by del t plus u bar dot product del omega bar is equal to omega bar dot del u bar plus 1 by R e del square omega bar. So, here R e is the Reynolds number, and then omega bar is the vorticity vector, and u bar is the velocity vector. So, this is one equation used in the velocity vorticity formulation, and the second equation used is del square u bar is equal to minus del cross omega bar as given in this equation B. So, there are two equations in the vectorial form as given in equations A and B. So, this equation, say for example, if we consider two dimensional problems, so that we can, these equations we can write as, for two dimensional omega is the vorticity. So, del omega by del t plus u into del omega by del x plus v into del omega by del y, that is equal to 1 by R e del square omega as in this equation, and then this corresponding to this equation here in two dimensions, we can write del square u is equal to minus del omega by del y, and say del square v is equal to minus del omega by del x as in this equation, and where omega is equal to del v by del x minus del u by del y. So, these equations gives the velocity vorticity formulation for the Navier-Stokes equation in 3 dimensions and 2 dimensions. So, here we have some advantages, like now the pressure is not directly coming. So, the expression, the equations are in terms of velocity and the vorticity. So, wherever the vorticity term is important, then if you use these equations, this form of the Navier-Stokes equation, it will be much easier, and then here generally for this formulation, velocity vorticity formulations, the boundary conditions will be in terms of the velocity. So, once we solve the vorticity transport and the Poisson equation corresponding to this equation B as here. So, if we solve this equation, we get the velocity distribution and the vorticity distribution throughout the domain. So, once we get the velocity and vorticity, then we can find out other parameters like pressure, we can find out from the say obtained values of the velocity and the vorticity. So, this velocity vorticity formulation is also used in many problems wherever we can express, we can use the parameter vorticity, and further these equations are much easier to solve compared to the primitive variables formulations which we have seen earlier. So, that is why wherever possible we prefer to use the velocity vorticity formulation of the Navier-Stokes equations. And now, the third formulation is vorticity stream function formulation. So, depending upon the problem, wherever we can write, we can express the stream function for the typical problem where we can express the stream function, then we use this formulation, vorticity stream function formulation. So, here also say if you consider, say for example, two dimensional problem, here we have two equations. The first equation is written like this, say del square omega is equal to Re into del omega by del t, say plus del by del x of del psi by del y into omega minus del by del y of del psi by del x into omega. So, this is equation, first equation A, and second equation is del square psi plus omega is equal to del psi by del t. So, here we have got two expressions. First one is equation A, where del square omega is equal to Re into del omega by del t plus del by del x of del psi by del y of omega minus del by del y of del psi by del x omega, and the second equation is given as del square psi plus omega is equal to del psi by del t. So, here the boundary conditions are in terms of psi, say psi is equal to psi b on gamma at the boundary, and then we can have its normal derivative del psi by del n is equal to del psi by del n at b. So, these are the can be the boundary conditions, and the equations, two equations, equation A and B, which is in terms of the say Reynolds number Re and the omega and the psi. So, we can solve this equation, two equations. So, we get the distribution of the stream function and the vorticity omega. So, depending upon the problem, this formulation also we can use, and then we can get a solution, and finally, once we get the omega and the psi, that means the vorticity and the stream function, then we can get other parameters like velocities and the pressure. So, typically say depending upon the problem. So, whether we can some problems it will be much easier to use the primitive variable formulation, some other case the velocity vorticity formulation will be easier, and some other case depending upon the problem we can utilize the vorticity stream function formulation. So, depending on the problem we have to choose the formulation, the Navier-Stokes formulation, and then we have to try to solve the problem, and then once the variables, whether in the primitive variable formulation directly we get the pressure and velocity, but in the say the velocity vorticity formulation we get in terms of the velocity and vorticity. So, then we may have to find out the pressure, and then the third formulation we get the in terms of vorticity and stream function, and then after getting the vorticity and stream function we may have to find out the velocity and the pressure distribution for the problem considered. So, depending upon the problem we can choose the particular formulation and then try to solve the problem. So, so far we have seen the Navier-Stokes equation derivation, and then the various analytical solutions, and then for the simplified cases, and also we have seen three kinds of formulations for the Navier-Stokes equations. As we have already discussed, the Navier-Stokes equation for the real field problems is very difficult to get exact solutions. So, we may have to go for the numerical solutions.